What's up, everybody? Mr. Cully coming at you with a video again, and I just want to recap a lesson that we went over about making ionic compounds and just kind of go through it for those of you that may want some extra help with it or just want to kind of get a refresher on it. So that's what we're going to discuss today. And right now up here I have a chart that we filled in the other day of the Lewis structures, the Lewis dot diagrams of certain elements. And so I just kind of want to recap this first. So here we have kind of like a smushed version of the periodic table. Now, if you look at the real periodic table, it's a lot bigger than this. But what we're doing is we're cutting out this huge middle red block here, and then we're kind of smushing it together. So that's what we're looking at in the PowerPoint. And I want you to notice something. So in this first column, this one right here with hydrogen and lithium and sodium and potassium, they have a dot. Well, that dot resembles that valence electron. And a valence electron, just remember, is the outermost electron. So if you notice, this whole column, each of them have one valence electron. And if you go one column over, each of these guys have two valence electrons. In another column over, they have 3 and 4 and 5 and 6 and 7 and 8. All right. The exception over here being helium, because remember, when we draw these out, helium, that first ring, can only fit 2. And helium is such a small element that it only has 2 electrons to begin with. But other than that, all the ones in this column are going to have 8 valence electrons, as shown by these dots that surround the abbreviation. All right. So then we talked about, okay, well, when these guys want to form compounds, remember, all of these elements want to have 8 in their outer shell. So hydrogen over here, it wants to get rid of that. Okay. Like hydrogen, lithium, sodium, potassium, like lithium, it's much easier for lithium to give its one away than to gain 7. All right. So lithium is going to want to give that electron away. Well, remember, electrons are negative. If you get something negative away, then you become more positive. The way I think about it is if you get something negative out of your life, then you become a more positive person. Well, same thing with electrons. When these elements give away electrons, they become more positive. Well, how many does lithium have to give away? Just 1. So what would a charge become? It would become +1. All right. So that's the case for all of these guys. They would have a +1 charge, +1 charge, +1 charge. Because if they were to form a bond, they would be giving that electron away. They would then become positively charged by 1. All right. Well, let's look at these guys that are one row or one column over. So beryllium, magnesium, calcium. They have 2 valence electrons. Remember, they want 8 total. Well, is it easier for them to give away 2 or to get 6? It's easy for them to give away 2. So they're going to give away 2. All right, they're going to give away 2. Remember, when they give away 2, they don't have 0. They technically have 8 again, because remember when we did the Bohr models, they have an outer shell. Well, that shell, once they give away those 2, it's going to have 8 again. It's kind of weird to think about, but anytime they give away, anytime one of these elements technically has 0 or 8, it's a full shell. So that's what's most important here. So don't get confused by that. But beryllium, magnesium, calcium, they're going to give away 2. Well, when you give away 2 negative electrons, you become especially more positive, even more positive than these guys. Because if you give away 2, then you then have a 2+ charge. Remember, they're giving away 2 negative particles, so they become positive by 2. All right, boron and aluminum. These guys have 3 valence electrons. Is it easier for them to give away 3 or to gain 5? Well, for them, it's still easier to give away those 3. So if you give away 3 electrons now, then you would have a 3+ charge or a +3 charge. Okay. Now this is kind of where it changes a little bit. So carbon and silicon, they have 4 valence electrons. Is it easier for them to gain 4 or to give away 4? Well, it can kind of go either way. So for these, we could just say positive or -4. They could either get, they can gain, they can give, either one. Doesn't matter. So we just say they can go either way, positive or -4. We don't actually form many ionic bonds with these anyway, so it's okay. All right, nitrogen. Nitrogen and phosphorus, this column right here, they each have 5 valence electrons, all right? And they want 8. So before we were giving electrons away, these guys, well, it's actually easier for them to gain than to give. Why? Because they already have 5. They're getting pretty close to 8. So instead of giving away their 5, they're going to gain 3. So remember, electrons are negative. If you gain something negative, you become a more negative person. If something bad happens to you that's negative, that's a bad thing. You become more negative. So instead of us giving away electrons and becoming more positive, these guys are going to gain, or sorry, yeah. Did I say that right the first time? I don't know. I have to go back and check. Nitrogen and phosphorus, they're going to gain electrons. They're going to gain 3 electrons to become more negative. So how much more negative would they become if they gain 3? 3 negative, or -3 charge. So these guys would have a -3 charge because they're gaining 3 electrons to get a full shell. Oxygen here, okay? Oxygen and sulfur, they have 6 valence electrons. Well, they want to get 2 more. Well, if you gain 2 electrons, which are both negative, then you're going to have a -2 charge, which we denote with 2 minus. Fluorine and chlorine, they want to get 1. They have 7 valence electrons. They want to get 1 more. They would have a 1 minus charge because if they gained 1 electron, they would become more negative by 1. And then helium, neon, and argon. Remember, these guys, they're content. They have full shells. So neon, argon, helium, they don't want any more. They're fine the way that they are. So they're not going to gain any. They're not going to get any. So their charge would be 0. They're going to stay neutral. All those guys are going to stay neutral. All right. So this chart is going to be hugely important for us when we start forming ionic compounds. We need to know the charges here, and we need to know how many valence electrons they have. All right, we're going to do it several ways. We're going to do a couple methods to kind of explain this. But one thing that I do want to point out is that these charges, these are what would their charge would be if they did form a compound. All right, so like if lithium did form a compound, it would give its electron away. That's the charge it would have. That's the case for all of these. There's a special name for that charge, and it's kind of nerdy sounding. Don't let it scare you. It's called the oxidation number. So the oxidation number is the charge of an atom when it has a full valence shell, and that happens after they bond. So it's basically what charge would these guys have after they bond? Well, we just wrote all those down. That's the charges that they would have after they form a bond with another element. All right, so we're going to be using this in the examples to come. Let's take a look. So ionic bonds, forming ionic compounds. Let's form an ionic compound with lithium and fluorine. Well, if you go back and you look, let's just look at what lithium would be. Lithium has 1 valence electron and fluorine has 7. All right, so I'm going to draw them out. I'm going to draw the Lewis dot diagrams for both of them. Lithium has 1 valence electron, which is right there. Fluorine has 7. So I'm going to draw the 7 valence electrons out. Just like this. All right. So I got both dot diagrams here. Now remember, lithium wants to give it away while fluorine wants to gain 1. Well, this is like a perfect match because fluorine has 1 spot to fill and lithium has 1 to give. So lithium wants to give its valence electron to fluorine. When it does that, it forms a bond. So what we do is we draw an arrow from that valence electron that lithium has to the space where it would be filled in fluorine's shell. So that's what we just did. Now, here's the thing. We want to find out, okay, what's the ratio? How many lithium atoms total did I need to make fluorine happy? Well, I just needed 1 because it was a perfect match. 1 lithium atom fit really well with 1 fluorine atom. So how would I write this compound then? Well, if I was writing the chemical formula, then it would just be Li. You could write the 1, F1. Because what this is saying is I needed 1 lithium atom to fit really well with that 1 fluorine atom. It was a 1-to-1 ratio. It was perfect. Now remember, when you have 1s in a chemical formula, you technically don't have to write them because it's just kind of implied. Kind of like in math when you have a problem like 1x plus 2y equals 4. You don't really write the 1s before the variables. It's just kind of implied. All right, so our answer here, what is the compound that's formed between lithium and fluorine? It'd be LiF. Well, you might ask which one comes first. Whichever one is giving the electron away comes first, okay? Whichever one gives it away. So it'd be LiF. All right, let's take a look at another example. Lithium and oxygen. All right, so lithium and oxygen. Well, lithium, if you go back and look at your chart, we just used it. It's got 1 valence electron. Oxygen has 6. So I'm going to draw my 6. All right, so now lithium has 1 to give, but how many does oxygen want? Oxygen wants 2 more, okay? Not 1 more like fluorine did, but 2 more. So now I got to think, okay, well, lithium can give its 1 to maybe that spot right there, but oxygen's still not happy. So what I got to do is I need to add another lithium. I need to add another lithium. because now I've got 2 total electrons to give to oxygen. So now the other lithium can donate and give it to oxygen. So now oxygen's happy. So now the question is, okay, what was my ratio? How many lithium atoms did I need to make that one oxygen atom happy? Well, I needed 2. So my chemical formula is going to be Li2O. That's it. Because I needed 2 lithium atoms to make oxygen have a full shell. So it would be Li2O. And that's it. All right, fair enough. Lithium and nitrogen now. Okay, so lithium, we're getting pretty good with lithium. Lithium has 1 valence electron. Nitrogen has 5 valence electrons. Well, I'm sure you can already guess. All right, it needs 3 more. So how many lithium atoms would I need to make nitrogen happy? And if you said 3, you'd be exactly right. Because remember, each lithium can donate 1 valence electron. So this one can donate 1 there, this one can donate 1 there, and this one can donate 1 there. So how many lithium did I need to make nitrogen happy? 3. So it'd be Li3. Oops, that looks like a weird 3. Li3N. Just like that. Li3N. All right, fair enough. Let's do this one. Magnesium and oxygen. All right, looking at that table that we filled out, magnesium has 2 valence electrons and oxygen has 6. So we'll fill it out like that. All right, so oxygen wants 2 more and magnesium has 2 to give. This is another perfect match. So really, I don't need to do anything. Magnesium can give both of its to oxygen and then they're both happy. It's a 1-to-1 ratio. So this one is just MgO, magnesium oxide. Perfect. All right, magnesium and chlorine. So magnesium, again, has 2 valence electrons, and chlorine has 7. So chlorine's got 7. Fill that in better. There we go. All right, so chlorine only wants 1 more, but magnesium has 2 more to give. So we're kind of running into a problem because if magnesium gave its 1 away to chlorine, I mean, chlorine's happy, but magnesium still has 1 left over. So what could we do here? Well, if we want another spot to fill, then we could add another chlorine atom. So if I add another chlorine down here, then I have another spot that I can fill. And now I can take that other electron that magnesium has and give it to chlorine. So now my ratio is I have 1 magnesium to 2 chlorine. All right, so sometimes you have to mess with the second element too. So now I've got 1 magnesium to 2 chlorine, so this would be MgCl2. All right, so 1 magnesium for every 2 chlorine. All right, so it can go both ways. It gets kind of tricky. All right, let's take a look at another one. Magnesium and nitrogen. All right, so magnesium, again, has 2 valence electrons. Nitrogen has 5. All right, fair enough. So, all right, let's take a look at what we need. So nitrogen has 5, so it needs 3 more valence electrons. Well, magnesium has 2 to give. All right, so that's kind of a problem, isn't it? Yeah, this is not going to be very clean like it has been. So magnesium can give its 1, right there, and can give another one to nitrogen. But so magnesium's happy, but nitrogen still needs another spot filled. So I'm going to need another magnesium, right? Yeah, I am. So I'm going to add another magnesium. All right, so that has 2 valence electrons. Okay, well, all right, so magnesium can give 1 to nitrogen, and so now nitrogen's happy. But now my second magnesium isn't happy because it still has 1 left over. Okay, this is getting kind of weird. So I need to add another nitrogen. Okay, because I still have more spots to fill. So now I have another nitrogen. I draw my 5 valence electrons. And now magnesium can give its second one to this nitrogen. And so now, all right, I still have 2 more spots to fill with nitrogen. And I don't have any magnesium left. Well, you know what? If I add another magnesium, which has 2 valence electrons, and this nitrogen has 2 more spots to fill, then I think I would be done, right? Yeah. So if I put those 2 electrons and I give them to that nitrogen, now I think I made everybody happy. Yeah, I have. So how many did I need of each to make this work? Well, I needed 3 magnesium, so it'd be Mg3, and I needed 2 nitrogen, so Mg3N2. All right, that one's kind of tough, but it still worked out either way. It doesn't really get more tough than that, but that does happen sometimes. So it was Mg3N2. All right, fair enough. Aluminum and oxygen. All right, so we'll do this one. Aluminum has 1, 2, 3, and oxygen has 1, 2, 3, 4, 5, 6. Okay. All right, well, let's see what happens. All right, oxygen. Oxygen wants 2 more valence electrons. Aluminum has 3 to give. So, all right, the first one of aluminum can go there. The second one can go there. And now oxygen's happy, but aluminum still has 1 left over. So I got to add another oxygen. So oxygen, again, has 6 valence electrons, which means that it has 2 spots to fill. So that last valence electron aluminum has can go in that spot. All right, so now aluminum's happy, but oxygen still has a spot to fill. All right, so I got to add another aluminum. All right, so aluminum has 3 valence electrons. Well, one of them can go make oxygen happy, but now I have 2 more left to give. Well, all right, again, this is going to kind of work out cleanly because if I add another oxygen, that has 2 spots that I need to fill. Well, that's perfect because now I have 2 spots to get, or 2 electrons to give. So I'm going to give the final 2 that aluminum has over to my final oxygen. And now I think everybody's happy. So what's my ratio here? It would be 2 aluminum for every 3 oxygen. So Al2O3. Boom. And that's it. So this is what we're working with, and we're looking for what is my ratio between how many of this atom do I need to make this atom happy. And sometimes you just have to keep adding them until it finally works out. So you'll eventually land in a place where you're like, okay, everyone's happy, and then you just count how many atoms that you need. So this is going to be the first step that we're going to use when we actually draw out the valence electrons and we see, okay, what is the compound that it's going to form? And so this is the first method that we're going to use. In a different video, I'm going to show you kind of like a simpler method. But for right now, we're just going to use this because for those that are visual learners, they like this a lot better. But stay tuned for another video.